Hello, chemistry girls. We are going to talk a little bit today about what are called buffer solutions. These notes go along with the beginning of chapter 14, so don't forget about your assignment to look over about the first 5 pages of chapter 14 to learn about buffers. Now, before we learn about buffers, we're just going to review a little bit about what we already know for weak acid and weak base substances. This is a little PowerPoint slide to help us visualize a weak acid, this imaginary HB substance. As we know, I put some of this into water, and the equilibrium that we can see here will be set up. HB molecules, a few of them, will interact with water and form some hydronium ion molecules and some B- ions. And down here, this is my beaker, and this is to help us visualize really everything that we've got going on in this beaker with the sizes of the letters to help us understand the relative amounts of everything. Of course, the gigantic H2O means that mostly what this is a beaker of water. Some of the water molecules are getting involved in this equilibrium process, but really most of them aren't. There's just many, many zillions of water molecules in the beaker here that just sit around and act as a solvent. So we have a lot of water. Of course, what we could also visualize inside the beaker here is these HB molecules, those that did not break apart, are floating in water. We, of course, would have the B- and the hydronium H3O pluses that are formed by the equilibrium. And here, very tiny, I don't know how well you can see it online, but I do have a very, very small little OH- hydroxide ion concentration, just to remind us that really acids and bases both are combinations of those two ions. It's just that for the acid solution, we focus on the H3O plus and we ignore the relatively teensy amount of OH- hydroxide that's present. So that one's highlighted in red, and as it says here, the solution would test with a pH of less than 7 because of the presence of the H3O plus, reminding us that we would need a Ka value to determine the exact pH, but we can pretty safely assume that it would have a pH on the negative side of 7. So in a letter form, we've got everything that we can find in this beaker after the equilibrium is set up. If I flip over here to my simulation from University of Colorado, this is one we looked at before, but this is actually a picture using the magnifying glass of what we were just talking about on the other page. My weak acid is an HA instead of HB, but it's the same idea. These dark gray molecules represent all of the HAs that are simply floating in water. I can turn on the water actually and show you that there's quite a few of them in there. And meanwhile, because of the equilibrium, we have created a few of the A- ions and hydronium ion, H3O plus. And we know that if we stick our pH paper in, what the pH paper is picking up on is the presence of the hydronium ion. And that's what gives this a negative pH of somewhere between 4 and 5, something like that. So not really the HAs that are floating in water. That's not what creates the acid situation. It's the presence of the hydronium H3O plus. So if we go back, here is a similar picture to remind us of the weak base situation. Many of you drew a picture with different symbols to represent something very much like this. Take a solid NABA substance, dissolve it in water, and we know that this is what will happen. First of all, the sodium dissolves into sodiums and B-. Then B- will interact with water and set up the equilibrium that we can see here. So by the time everything is finished, what would we have floating in our beaker here? Well, of course, once again, we would have a relatively large amount of water. However, we can also find those sodium ions, and I've put them in gray here because they're not really part of the equilibrium. They don't really have any effect on anything, but they are present in the beaker because I dissolved sodium bromide, so now I have sodium. So that's present. Of course, B- is present, meaning those ions of B- that did not interact with water. Those that did formed HB molecules and OH-, highlighted in blue here because, again, we would expect pH paper to pick up on the presence of the OH minus, or a pH meter, whatever we want to use. Expect the solution to test with a pH on above 7 on the basic side of the pH range. And finally, we have our teensy insignificant amount of H3O+ that's also present in any solution. Here's what we have at the University of Colorado simulation. This again shows us with the magnifying glass here that we have our B ion, our B substances in water here, interacting with water to form a few HBs and a few hydroxides. Using the pH paper, the presence of the hydroxides would be detected, and this would be reported to have a pH of around 9 or something like that.